Hello and welcome to this course on solid-state physics. My name is Simo Huotari and I'm a professor in materials physics at the University of Helsinki. These video lectures are a part of our 10 ECTS credit master level course on solid-state physics, and the course is a part of our master program in materials research. First of all, why to study solid-state physics? Well, solid-state physics is definitely a backbone to our modern society. Most technological advances rely in a way or another on solid-state physics. All your fancy mobile telephones, your computers and such, are based on electronics, which is based on solid-state physics. The broader field of condensed matter physics includes also the physics of soft condensed matter, the study of liquids, also liquid metals, polymers, life materials, such as those that constitute our own bodies. The solid-state physics itself could have been said to have started from the discovery of X-rays by Wilhelm Röntgen, and soon it was used to study the structure of crystals. Also, the double helix structure of DNA was found by using solid-state physics and its subfield of crystallography. Here is an example of a case where several aspects of solid-state physics are in play together. We have here a model of a thin-film solar cell. The ultimate purpose of a solar cell panel is to convert sunlight into electricity. It must contain some material that absorbs sunlight efficiently and that converts the absorbed photons into electrons and holes that can be used for practical applications to do work. To collect the electrons and holes, we must have conductive current collectors. But at least one of the current collectors should be transparent. Here's a complex problem, since from everyday life we know that electric conductors such as metals are not usually transparent. Metals are highly reflective, which makes them shiny. We will come back to this point, that is, why metals are shiny, later on during this course. Most transparent materials in turn are insulators, such as the regular window glass, for example. A transparent conductor seems like a paradox, which it actually is. We will thoroughly learn during this course why it is a paradox, but here we do have a quite untypical material, indium tin oxide, which is both transparent and conducting at the same time. It belongs to a class of solid-state materials called transparent conductive oxides. To examine how this material works, we must first understand its crystal structure, which allows us to construct its electron band structure and the types of states of the valence electrons. Only then we can understand why it is optically transparent and at the same time can conduct a current. We'll also have lots of fun, for example by playing with liquid nitrogen. And that's because the energy scales of many interesting phenomena in solid-state physics compete with the thermal energy. So we will learn, for example, what is superconductivity and how it works. Well, at least up to the point that the modern solid-state physics understands it. And we will learn also other new emerging phenomena that take place when atoms are put together and allowed to interact with each other. For example, completely new types of particles can emerge. Electrons with unusual mass and charge, Cooper pairs and other quasiparticles, particles that are neither fermions nor bosons, and particles that are their own antiparticles, and many more. After this course, you will have learned at least the following. You will understand the different kinds of interatomic bonding mechanisms and describe how they affect the properties of materials. You can recognize and describe different crystal structures and understand basic crystallography. You can apply diffraction methods to determine crystallographic quantities. You can apply the concept of reciprocal lattice to crystallography, as well as describing phonon and electron states in crystals, as well as quasiparticles. You can describe what phonons are and describe their relation to dynamic properties of materials. You can explain the ways how solids can store energy, and you can apply quantum mechanical electron models to predict optical and transport properties of metals and semiconductors you will learn thoroughly the physics of semiconductors and semiconductor devices. You will be able to understand and explain the physical principles of electric and magnetic phenomena in solids. You will understand the basic of superconductivity and related phenomena, and you can apply the electron gas theory to explain phenomena in low-dimensional electron systems. Again, welcome to this course, and thanks for watching this introductory video. Next, we will turn our attention to interatomic bonding.